So that's why a lot of the engines are starting to have smaller patterns of the degrees that they're versus the conventional 360-degree groove.
Okay. So we're going to find more of these modern style bearings in the LSs, the LT platform, the
Correct.
Coyotes, the Gen 3 HEMI. Okay.
You're right.
Okay.
Right.
Yeah, going back to that 2050 weight, I'm thinking of my dad when he was running a drag boat with my uncle, and they had a blown big block, and that's all they ran.
And if you run, what happens is people that run the thin oil with a 360-degree groove, I have studies where the oil flow is so much at low speeds it can never catch up. So you technically can run the engine without enough oil to lubricate and create that film pressure, because the oil pump capacity cannot keep up with at low speed, and it never catches up as the RPMs go up.
Oh, interesting. Well, that kind of kills a myth that kind of floats around there, that as that RPM is going up, no matter what, we're going to get more oil pressure, more oil flow, and not always the case.
It's not always the case, because the amount of oil that it's using, again, oil pressure is resistance to flow. That's the key. So if you don't have enough capacity to pump it, and you run a 360, an old bearing, and you say, oh, I'm going to build this engine and I'm going to put thin oil in there and make more horsepower, because it is a parasitic drag. But if you take that and you don't consider that you don't have enough capacity to flow enough oil, you can run the rod bearing. As I said earlier, the amount of how this works with the degrees, there's engineering that goes into this, how much oil is going to feed the rod bearings, because the main bearing, the crankshaft, is what feeds the rod bearings. So in this case, you have rod bearings, there's no groove, because it's getting the oil through the crankshaft to feed here. So that is relative to the groove and the phasing, which will feed the rod bearing or not feed the rod bearing.
So again, everything here is a system, and nothing can be chosen in exclusion. We have to work from our main bearings out to our rod bearings, or do we actually sometimes work backwards?
It's important to know both. I always tell everybody, it's like, look, we need to know where we want to be before we start. Okay. So what oil do you want to run? All right. If you're going to run thin oil, the groove is very important to know. And then clearances. Again, if you have big clearances, there's less resistance to create that pressure, because it's just going to flow out the sides, because there's nothing to keep oil pressure here other than that space.
Right.
So as you run if you have too much clearance and too thin of oil, it's going to take the path of least resistance, so you don't get the film pressure. Now, a crankshaft to a bearing in thinner oil applications with the 530 or nowadays even thinner than that, we're talking from the crankshaft to the bearing microns of film thickness. Microns. So you can't do that with thick oil, and you can't take thick oil and do that either way. You have to build the system.
Yeah.
So there's a rule of thumb, 1,000 per inch of shaft diameter. It's a rule of thumb for measurements. And I say, and that's a good rule. Typically, when I talk to somebody, if they want to run a thinner oil, I lean to the shorter side. Okay. The smaller side of clearance. And if I want to run thick oil, to the bigger side of that. And that way it creates how much opening, how much clearance you have, which is the flow. But you also need a certain amount of flow, because a typical bearing has, like this is a copper tin lead, and you have every element has a melting point. So if you don't get enough flow and you get frictional temperature, you start melting the components out of it.
Okay.
So aluminum has a much higher melting point than copper tin lead, but aluminum, when it fails, wants to grab.
Oh, all right.
It doesn't work real well. Tin is your friend here.
Okay. So when it melts, it actually almost creates a backup lubricity, if you will.
And once it heats, it grows, and you get frictional temperature, and then it just snowballs into an engine failure.
Right. Okay. So, maybe not quite so as catastrophic as an aluminum bearing failure.
Yes.
But so going into the bearings and the different grooves, the different oils, there's a lot to be considered if I'm building a nitrous engine, big block Chevy, throwing a ton of it down its throat, versus building a high RPM 410 sprint car motor. We need to know really what we're doing, what we're pumping into the oil that could break down the oil, the different fuels that could wash down. So all of that takes a play in our decision making as we're building out this entire system.
Yeah, definitely. Knowing what bearing is, again, if it's a stock application, aluminum bearing works perfect. You know, if it came, and if the engineers at the OE designed it with an aluminum bearing, you know, a round aluminum bearing. You know, the one thing we didn't talk about is the start-stop engines.
Oh,
so,
yeah.
you know, that's a whole nother element, because the start-stop, every time that engine shuts off, it does not have an oil film.
Right.
So in certain applications, I have some studies on this as well. The number 5 main bearing can run 3 to 3.5 seconds and up to 600 RPMs every time that engine starts. So every red light you hit, that engine shuts off. It runs 3.5 seconds before you get any oil to create that film. So a polymer bearing has, basically it's kind of a bimetal bearing. It's a steel, but has a resin with a wear agent in there. A lot of them use aluminum oxide, and that's your wear pattern on there. So, and aluminum again has a higher melting point. So the polymer is another one. But back to the question of what would you use based off what your engine is. You know, you have to know if you're building a lot of power. You know, believe it or not, a nitrous motor and a 410 Sprint, I would basically use the same thing. I would use a tri-metal bearing. Copper tin lead.
That's surprising. I learn something new every day.
I would. The thing between the two is a sprint car doesn't go through the harmonics as a big cubic inch nitrous motor and create crank flex.
Okay.
So you have to open up clearances based off crank flex. When you open up clearance, now you open up the leakage for the film pressure. So a lot of times that's why they have to run thicker oil, is because you can't run thin oil with big clearances because you can't create film pressure.
Sure.
So that's kind of the difference in there. You know, the other thing is on these bearings right here. This is a tri-metal bearing and it's a coated bearing.
Okay.
So there's another layer of coating over the copper tin lead.
Okay.
All right. Remember I said copper tin lead, everything has a melting point.
Sure.
So when you get frictional temperature, because you don't have oil film between the journal and the bearing, you start getting frictional temperature and it starts to melt the components out of the plating. It's electroplating. You start melting the components out of there. Every component has one. The coating bearing creates another thermal barrier. So it creates a protection to the properties the heat can't get to there. And the other thing is, coatings typically are a moly base, so it's a dry film lubricant.
Okay.
So when you do get contact, the moly is exactly that. It's a dry film lubricant.
Sure.
So when you get contact, it will allow it to hit and not seize, unless it hits too bad, to a point.
Sure.
To a point. And it's a great insurance. I love coated bearings on applications like that when you get crank flex or oil films not enough. And it protects it, and it also keeps the heat from penetrating into there, and the bearing will last longer. So a coated bearing is another thing. Also works great on start-stop engines. It's another way of doing it.
Excellent news. Okay, cool. So you're seeing a lot of this, again, OE technology. The start-stop bearings are starting to bleed back into performance engines. We're learning a lot from that and bringing it in over to performance.
Yeah, there's a lot. The start-stop, because typically when you start an engine, it grates on an oil film from this time you start to the time you shut off, and it works perfect.
Yeah.
It's a perfect world.
Sure.
Because
you've got a column of oil being shoved against the backside of that bearing and all those.
Non-stop. And so then when you get to start-stop, I mean, they do it conserve fuel, you know, and that's a whole nother subject. But from a bearing manufacturer, it's a nightmare, because every time it stops, you have to reestablish that film pressure to keep the shaft, the crankshaft, and the bearing apart. If not, you end up with a failure.
Yeah. Okay.
So, you know, those are things we look at on the OE platform, as far as how can you create, what can you do to not have the melting of components? And then the other thing with polymer bearings and start-stop technology, there's no lead. So lead is your friend in the aftermarket, but in the OE world, they can't use lead.
Gotcha.
The only thing lead in there is typically a battery.
Yeah.
So we're not allowed to use lead in the OE world. And so we have to come up with how we'd make things work in the aftermarket. Typically speaking, a tri-metal bearing like this, no matter what manufacturer, is a copper tin lead. That is the plating, it's electroplating of copper tin lead. Now, different manufacturers will show different different percentages of copper tin lead, and based off what they feel is the best seizure resistance, load bearing capacity, et cetera, et cetera. But all the manufacturers use a copper tin lead in the aftermarket, and just different percentages of whether all the manufacturers use an aluminum bearing.
Yeah.
It's great for a stock replacement bearing that they can just put in there because hey, you gotta go to church on Sunday and pick up groceries, and it works, right? It just keeps going. So and different manufacturers put a suffix at the end, and the suffix typically will determine what that plating is, and some of the geometric, whoa, I have a hard time saying that one, geometric configurations of the bearing, which we will talk about later, because there's a whole lot to talk about that as well.
Yeah, getting into the ring flex and all of that.
Yes.
And okay. Well, greatly appreciate your information here. I've learned a lot today. I hope you guys have too. Stay tuned. We're going to be going through a couple more episodes here, getting into a deeper dive on engine bearings, and Dan's going to be teaching us a lot more. Look forward to it.